Alright guys, in this video, I'm going to do a summary of every single curly arrow mechanism you need to know for organic chemistry under the AQA A-level chemistry specification. Alright? I'm not going to go into the very fine details of forming reagents, catalysts, all that sort of stuff, but I'm going to go through everything you need to do regarding drawing the actual mechanism to get the marks on your paper. So let's start with nucleophilic substitution, okay? And this is where you're going to start with a haloalkane or a halogenoalkane, however you want to call it, it's completely fine. So I'm going to use the example of bromine. You could also use chlorine, that's completely fine. These are the most common ones you're going to see, okay? Bromine or chlorine. So nucleophilic substitution, it's pretty self-explanatory. We're going to have a nucleophile attacking this central carbon here, whatever the relatively positive carbon is attached to the halogen, and it's going to substitute that halogen for whatever the nucleophile is, okay? And there are three main nucleophiles we need to be aware of. So as I mentioned, there's going to be a delta positive and a delta negative dipole existing here due to the electronegativity of the bromine. All right, so before I actually jump into the mechanism itself, I'm going to give you some really useful knowledge that I just wish I knew when it came on to answering these mechanisms, right? What does a curly arrow show us? A two-headed arrow. It's showing us the movement of a pair of electrons, okay? And this is either going to be from a lone pair like this onto something else, donating its lone pair. So let's say we're using our example of OH minus, right? You're going to be donating your lone pair onto something else in order to form a dative covalent bond. Okay, now you don't want to say this in your responses because it's not in the spec, but this is what is happening. Okay, you're forming a covalent bond, specifically a dative bond. You're donating both of the electrons in this lone pair to form a covalent bond, right? So you're either doing that or you're breaking a bond and showing the movement of the electrons in a different way. So you have a bond here, you're going to be showing this bond breaking and going on to something else. I'm just going to show it as the symbol X. Okay, so that's all a curly arrow mechanism is. It's either showing the forming or breaking of covalent bonds. Okay, so get your head wrapped around that, and it should make the rest of these videos pretty simple. You just have to remember the nucleophiles and electrophiles involved, and we should be fine. Let's start with the hydroxide. We're going to have our OH minus, making sure to draw our lone pair. So make sure you're drawing the arrow starting from the lone pair. Don't start over here or something like that. Or from the negative. Always start it from the lone pair. Okay, that's where the electrons are traveling from. And we're going on to this delta positive carbon right here. Now, this carbon is now going to have 5 bonds. Essentially, and it doesn't want that. It's group 4, so it's going to become energetically unstable. So this is going to become our leaving group, and the electron pair within this covalent bond is going to be donated onto this bromide ion. Okay, so we're going to be forming our product here: H3C, C, H, H. The bromide ion has left in solution, and we have formed an alcohol. Okay, and then we're going to have our bromide ion going off in solution. Now, these delta positive and delta negative charges, you don't need to show this in your exam, but you do need to understand the theory regarding dipoles, electronegativity, and how it determines the leaving group, etc. But I'm not going to cover that in this video. Okay, so that's our hydroxide nucleophile out the way. Let's go on to cyanide, and it's literally as simple as this, guys. So if I rub this out, I can just replace these two with the cyanide ion, exactly the same thing, right? So we'd have our Cn here and Cn here. Literally exactly the same thing, just a different nucleophile. So our third nucleophile is slightly different. We're dealing with ammonia here, and there's an intermediate stage. All right, so let's draw this out. We'd have our nucleophile, ammonia, coming in, attacking the carbon, and then we're going to have it bonding onto here. Now I'm going to show the hydrogen bonds here just to signify what's going on. And then again, we're going to have our bromide ion off in solution. Now, this nitrogen is not going to be happy with having 4 bonds around it. It only wants 3, okay? So it's going to become positive because it formed a dative covalent bond. It donated both of the electrons in this lone pair, okay? So this is positive. Now, one of these hydrogens is going to be like, you know what? Take my electron. It's all good. And it's going to donate it onto the nitrogen, okay? It can be any of these three hydrogens. It honestly doesn't matter. Just pick one, draw the curly arrow, and you'll be fine. And this is going to form us our product here. Do you remember what this functional group is called? This is a primary amine, okay? And you're going to have your ammonium bromide. Okay? The reason that you get ammonium bromide is that this hydrogen that leaves is actually reacting with the NH3. So you've got more ammonia in solution, okay? This is going to attack this, break this off, and it's going to form the ammonium ion, which is going to react with the bromide ion, and it's going to form ammonium bromide, okay? But you don't need to show that. All you need to show is this right here, okay? Now, you need to be aware that we can get subsequent nucleophilic substitution reactions occurring here. And why is that? The reason being is that this product that we form, this primary amine, because nitrogen is group 5, we're going to have a lone pair on this nitrogen here because it's just been donated back by this hydrogen. Okay, so you got to keep that in mind. So what can happen here is this can act as a subsequent nucleophile, attack the initial reagent here, and carry out additional substitution reactions, okay? So let's draw that out quickly and we can look at how we form a secondary amine in this way. Before we move on to the secondary amine formation in the subsequent nucleophilic substitution reactions, I realized that I left this negative charge here when I was dealing with the hydroxide ion and the cyanide ion. This is incorrect, okay? There is no negative charge on the ammonia. Really keep that in mind, my mistake there. So with that done then, let's draw our product that was formed, our primary amine in the previous nucleophilic substitution, coming in and attacking this haloalkane. So we'd have our NH2, CH2, CH3 that was formed previously, and this is going to come in and attack this relatively positive carbon. The bromine is going to be our leaving group again. Nothing else has changed here. So very similar to our ammonia example, we're going to be having a positive charge on the nitrogen here in the amine. So the ammonia that was present initially is going to come in with its lone pair, attack this hydrogen. This is going to break off onto here, donate its electron pair onto the nitrogen to make it neutral again, okay? And what we're going to form, we're going to form a secondary amine, okay? So it's going to be CH3, CH2, N, then we're going to have our H, and then the rest of the molecule here, CH2, CH3. Again, same thing, this NH4 that formed is going to react with this, forming ammonium bromide, okay? And this is a secondary amine because there's 2 carbon chains on nitrogen. But it doesn't stop there, guys. We can actually form a tertiary amine and a quaternary amine as well. Now, quaternary amine is not actually called a quaternary amine. It's called a quaternary ammonium salt. Okay, and that's due to the charge on the nitrogen. So what I'm going to do is I'm actually going to show how simple this is and keep the mechanism the same, but just changing our nucleophile. So in this instance, from the previous mechanism, it was a primary amine. I'm going to change this to be our product, our secondary amine, okay? So it's going to be our NH, then we're going to have our 1 carbon chain, CH2, CH3, and then the other carbon chain, CH2, CH3. All right, so this is our secondary amine acting as a nucleophile, coming in, attacking the carbon, bromine leaves, exactly the same thing here. And all I'm going to switch up in our intermediate is the fact that this hydrogen is now an ethyl chain, CH2, CH3. And then in our final product, this is no longer a hydrogen, okay? It's going to be another ethyl chain, CH2, CH3, as we can see in our molecule here. So if I rub this out quickly, so we can have space to add it in, CH2, CH3. Okay, this is a tertiary amine. That is our product in this case. As I mentioned, it doesn't stop there. You can react subsequently with this tertiary amine to form a quaternary ammonium salt. Okay, so let's do that right now. We rub this H out and change it for a third ethyl chain, CH2, CH3. We're not actually going to get our intermediate. Our intermediate is going to be our product. So let's rub this out to make that very clear. Rub this out as well. We're not going to get subsequent reactions occurring. This is our final product. So our ethyl chain is going to slot onto here instead of being a hydrogen. Okay. So it's a bit messy, but that is essentially how we would form a quaternary ammonium salt with nucleophilic substitution. And these are all subsequent reactions, okay, that occur in the instance of ammonia. Okay, so still on the topic of halo or halogenoalkanes, let's look at elimination reactions, okay? And this is going to be with hydroxide ions again. So let's draw out our starting reactant. So we've got a haloalkane here, right? We're going to have our hydroxide ion coming in and attacking one of these hydrogens, all right? And we're going to be forming a double bond because our product is an alkene. So I'm going to do it coming from over here, all right? So I'm going to go, this lone pair is going to be attacking this hydrogen, donating its lone pair to form a bond. This is going to be leaving the molecule, and then this covalent bond right here is like, what the hell do I do now if this hydrogen's leaving? It donates the pair onto this single bond here, this saturated carbon-carbon bond, to form a double bond, okay? Now, very similar to nucleophilic substitution, if we add in an additional bond here, an additional pair of electrons, this carbon-bromine bond is delta positive and delta negative. There is a dipole here, region of electronegativity on this bromine because it's a halogen. So this covalent bond is going to break off and the electrons are going to go onto the bromine. It's going to be our leaving group, okay? So that's a real easy one there. Now, you just have to get comfortable with the fact that if this hydroxide ion is attacking one of the hydrogens, the covalent bond between the carbon and the respective hydrogen is going to break off and form a double bond. Just remember that because this can happen from either side. For example, let's say we switch this up and we wanted to attack this hydrogen right here, which can definitely happen, okay? So let's say we had our hydroxide ion again, comes in, attacks this hydrogen. Now at this stage you might be like, oh man, like what do I do here? Just remember that the bond between the carbon and the hydrogen that's being attacked is going to break off and form a double bond. Where does the double bond form? The double bond is going to form to the adjacent side of the carbon. So in this instance, we're attacking this methyl group right here, right? So the double bond is going to form here. Now, if we were attacking one of the hydrogens on this methyl, the double bond is going to form here. Okay, just keep that in mind. But that is the gist of elimination of a halogenoalkane or a haloalkane with hydroxide ions. Right, so we formed an alkene right here. So let's draw that out real quick because I forgot to draw the product here. So it's going to be CH3, C. In this instance, the double bond was formed in the center. So it's going to be like this. There's going to be a hydrogen here and then a hydrogen here, hydrogen here. Okay, and then our bromine again is going to go off in solution. And this is going to form water. So we'd have plus H2O. Okay, simple as that. So on the topic of alkenes then, what mechanism do we need to know for alkenes? We need to know electrophilic addition. Okay, you also need to know acid catalyzed addition for the hydration of ethene, but we'll look at that after. Electrophilic addition is what we're going to focus on here. So what is an electrophile? The opposite of a nucleophile is an electron pair acceptor. And with electrophiles, you're always going to be dealing with regions of electron density. Okay, they love that negativity. And an alkene is perfect for that because this CC double bond here, there are 2 electrons per bond. Okay, so this is a region of 4 electrons essentially, which is very electron dense and very negative. Okay, so if we draw out the remainder of this molecule, I'm going to be using ethene as our example here to make it simple for us. What electrophiles do you need to know? Okay, you need to know diatomic halogens. So for example, Cl2, Br2, etc. It's going to look like this. You need to know a hydrogen halide. So for example, hydrogen bromide, hydrogen chloride. So let's draw it like this. And you also need to know sulfuric acid, H2SO4. Okay, so let's break down those one by one and see what's going on here. All right, I'm going to show you the way that I remember it, and I think it makes it as simple as possible. So you can simply just replace one electrophile with another. So let's start with our diatomic halogen. So I'm going to use the example of bromine, but you can use chlorine as well. That's completely fine. So we've got our diatomic bromine here bonded by a covalent bond. And there is actually a dipole present. You may not think it because they're identical atoms, but there is a delta positive here and a delta negative. Again, you don't need to show this in your exam. I'm just explaining it so you can understand why the arrows are moving where they're moving. So the electrons in this double bond are actually going to repel the electrons in this covalent bond right here and induces this dipole. Okay, that's how it works. So the closest atom is going to be relatively positive and the atom furthest away is going to be relatively negative. Okay, so it's going to induce that dipole here. Now what's going to happen is an electron pair in this double covalent bond is going to be attracted onto this relatively positive bromine. And then this other relatively negative bromine is going to break off like this. Okay, so that's our first two curly arrows. The electron dense double bond is attracted onto the bromine here, this first bromine atom, which is relatively positive, and then that is going to form a covalent bond here, and then this bond is going to break. The electrons are going to go onto this bromine, and it's going to go off in solution as a bromide ion. Okay, really important to keep that in mind. So we're going to form an intermediate here. Okay, this intermediate for these electrophilic additions is always going to be a carbocation. Okay, you're going to get varying types. You're going to get primary, secondary, or tertiary carbocations, and they all have varying stabilities, which is something you need to know, but I'm not going to cover it in this video because it goes into quite a bit of detail. So this double bond breaks, okay, and we're going to be left with a single carbon bond, but this bromine has now bonded on to one of these carbons. So I'm going to draw it right here. So we have a bromine down there, hydrogen here, hydrogen here. Now this poor carbon, right, it's lost its double bond here, so it's only going to have 3 bonds. Still got the 2 hydrogens, but it's lost its double bond, so it's not a happy guy. It wants 4 bonds to fulfill that octet, those 8 outer shell electrons, but it's going to have a positive charge here because it's essentially lost one of its electrons here, so it's been oxidized, right? You can essentially think of it like that. So what happens now is, because this is hella positive, all right, this is not delta positive, it's not relatively positive to the surrounding atoms, it is full on a cation, right? So what's going to happen is this bromide ion that broke off is going to come in and be like, you know what, I'm getting some revenge here, you took my best mate, and it is going to attack this carbon to be reunited and form our product. What is our product going to be? I'm going to draw it out real quickly, going to have to do it a bit smaller because I ran out of space. So it's going to be our C, H, 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 and then the bromide ions are reunited. All right, so dibromoethane. This is our product. Okay, so that's the reaction with a diatomic halogen out of the way. Let's look at the reaction with a hydrogen halide. Very similar process, and I'm going to try and make it as simple as possible for you guys. And you're going to see right now how identical it really is. So let's rub out our products real quick so you can see what's going on here. So with a hydrogen bromide or a hydrogen chloride, all we're going to do is we're going to change one of these starting atoms. Okay, so we're going to switch out one of the diatomic bromines is going to become a hydrogen. Okay, now these are no longer identical, so we're actually going to get a dipole existing already because a halogen is far more electronegative than a hydrogen. So there's going to be a dipole existing here regardless of this. All right, but we're going to get the same thing occurring. Okay, this region of electron density is attracted to this relatively positive hydrogen, and this bromine is kicked off and accepts the electrons in this covalent bond. So it has a lone pair on it, right? So in our previous mechanism, we had a bromine here. Easy peasy, that is just replaced with a hydrogen. Okay, exact same thing occurs here. This bromide ion that was kicked off is going to come in. It's mega attracted to this positive carbocation, and we're forming our product. Okay, so I'll draw out our product real quick. We're going to have CH3, CHHBr. Okay, bromoethane right here. We're going from an alkene to a halogenoalkane or a haloalkane, however you want to call it. Okay, so it's not a dihaloalkane, it's just a single haloalkane. Right, so next one, sulfuric acid. Now, again, I'm going to make this as easy as I possibly can for you guys. Let's rub this out and just replace it with our H2SO4. Now, I like to draw it like this, okay? So let's rub this out. You can draw the full molecule. So if you have your H2SO4, you're going to have your S, O, OH, OH. Okay, that's our H2SO4. I don't advise doing this just to make it easier for you guys. What you want to do is you want to start with the hydrogen here, just like with your hydrogen halide, and then you want the remainder of the sulfuric acid molecule drawn out like this, OSO2, OH. Okay, makes it real easy for you because you can think of the OSO2, OH as the halide. So for example, bromide ion. Okay, and just replace that with the OSO2, OH. We're going to get exactly the same thing occurring here. We're going to get a dipole between the relatively positive hydrogen and the relatively negative oxygen within the sulfuric acid molecule. Pretty simple here, hopefully. And then we're going to get exactly the same thing occurring, whereby the hydrogen is bonded onto one of these carbons, the double bond is broken, and then instead of a bromide ion coming in, we're going to get the remainder of the sulfuric acid coming in that broke off of this molecule here. So it's going to be OSO2OH minus, okay, so HSO4 minus, that is that right there, but just written out in a slightly weird format. But that's how you can do it. You can do that in your exam, completely fine. AQA will give you the marks, and it saves you having to draw out the full structure. And then our product is going to just be H3C, C, H2, and then we're going to have our OSO2OH molecule there. Okay, a bit squished up, but hopefully you get the idea. And what is this product referred to as? It's going to be referred to as an alkyl hydrogen sulfate. Okay. Right, next up, we've got another one involving alkenes, specifically ethene. Okay, so I'm going to use this as our starting molecule. Rub all this out. So we've got the hydration of ethene here, okay? So what's going to happen is we have a H plus here, all right? And this comes from our strong acid, phosphoric acid, okay? Concentrated phosphoric acid, which is H3PO4, if you weren't aware. And this region of electron density is going to be attracted to this positive hydrogen ion, okay? So this double bond here, one of these bonds is going to break, and we're going to form our intermediate here. So I'm going to try and stick to the same colors so you can see what's going on. Then we're going to have our hydrogen here that came from this starting hydrogen ion. And what's missing here is a positive on the carbon because it's only got 3 bonds now instead of 4. So it's a carbocation. The next thing that happens is water comes in, right? So we've got a water molecule here with a lone pair on it and 2 hydrogens attached. This comes in, donates its lone pair onto this carbocation, forming a dative covalent bond. And we're going to get another intermediate here. Let's draw this out. So we've got H3C, C, H, H, and then we've got the OH that just bonded on. Let's switch up the color so you can see what's going on. Now, because it formed a dative covalent bond, it's lost 1 electron essentially. It's been oxidized, so it has a positive charge. It doesn't like it, guys. It wants to be stable. It wants to be neutral. So one of these hydrogens, one of his best mates is like, you know what? Take my electron. It's all good. You can get back to being neutral. And we're going to form our final product here. What is that going to be? I know this is a bit messy, but hopefully you can follow me. It's going to be an alcohol. Okay, so we're going to have our CH3, CH2, OH. Okay, and this hydrogen goes off, plus H plus, and reforms the catalyst H3PO4. Okay? Okay, so that's haloalkanes and alkenes out the way. Let's take a look at alcohols. There's only one main mechanism you need to know here, and that is the acid catalyzed elimination reaction for the formation of an alkene from an alcohol. Okay, so let's draw our starting reactant out. So we're going to have our OH group on the end here for our alcohol, and there's a lone pair on this oxygen, okay? This is going to be attracted to a hydrogen ion, okay? This hydrogen ion comes from a concentrated strong acid. So it can be sulfuric acid or phosphoric acid, similar to our previous mechanism. So the hydrogen ion is going to come from that. This is attracted to this positive hydrogen ion, and it's going to form a dative covalent bond here. So let's draw out what our intermediate is going to be. I'm going to show all the hydrogens bonded onto the carbon this time, instead of just shorten it to a CH3 methyl group. So we're going to have our CH, H, and now the oxygen has got an additional hydrogen on it. So we're going to have like this, okay? So the carbons are happy, they've got 4 bonds each, but the oxygen is not happy because it just formed a dative covalent bond and essentially lost one of its electrons. Okay, so what we have to do is we have to signify that it now has a positive charge. So this carbon's like, you know what, mate, you're really unhappy, you're bringing down the vibes, I'm just going to donate my electron onto you. So you're happy, and then this goes off as water in the solution. And one of these hydrogens is going to donate its lone pair and form a double bond. Okay, what is our final product going to be? It's going to be an alkene. Okay, so in this example, it's just going to be ethene, but it will change depending on what your starting alcohol is, how many carbons there are in the chain, etc. And then this hydrogen that left the molecule is going to be a H+ ion, and it's going to reform the concentrated strong acid, so either our H2SO4 or our H3PO4. So one of these two is going to act as a catalyst and be reformed. Okay, so next up, we're going to be having mechanisms involving ketones and aldehydes, right? And the only mechanism for this is nucleophilic addition. We're going to have 2 separate nucleophiles. You're either going to have a negative hydride ion or you're going to have a CN cyanide ion. Now, let's draw out our starting reactant here. I'm going to use the example of propanone, right? This is a ketone. If you want to switch this up to be an aldehyde, we just swap the end carbon chain for a hydrogen to denote this functional group, which is an aldehyde. But I'm going to show them with a ketone in this example. So as I mentioned, the first nucleophile we're dealing with here is a hydride ion, which is a negative hydrogen ion, okay? So this is going to come in, and very similar to our previous examples, oxygen, very electronegative atom. When you see an oxygen, you should straight away think, okay, this is electronegative, and whatever is bonded to it is most likely going to be relatively positive. You're going to get a dipole forming. So this hydride ion, this negative ion, is attracted to this region of electron positivity, well, relative positivity in this dipole, and then this double bond here is going to break and donate its pair of electrons onto the oxygen. Okay, so let's look at our intermediate that's formed. We're going to be having the CH3 again, C, CH3. Remember, this is a ketone in our starting example, but if you want to swap it for an aldehyde, it would just be a H. Remember that, okay? So this is now going to be a single bonded oxygen. It has gained the electron pair here, which you need to signify, and it's gained 1 negative charge because one of the electrons originally belonged to him, but it's gained the additional one from the carbon. So you have to show the lone pair as well as the negative charge. And then this hydrogen has bonded onto the carbon right here. Okay. I know I'm keeping my colors pretty inconsistent, but hopefully you get the idea. Now what's going to happen here is this oxygen is going to react with another hydrogen ion. Okay. And this is going to come from solution, either a weak acid or water. So this is going to form a dative covalent bond with hydrogen and ultimately form an alcohol. Okay, so let's draw that out down here. What is our final product going to be? It's going to be H3C, C, CH3, H, OH. Okay, that is our final product here, an alcohol. So next up, remember I said we're dealing with a cyanide ion. So how does this differ? Very similar, okay? Let's rub out this H and replace it with a CN, okay? A little tip here that they mentioned in the mark scheme is, let's say you were doing the cyanide from this side, okay, CN. You always want to show the lone pair and the negative charge on the respective ion. So for example, the negative charge and the lone pair is not going to be on the nitrogen ever. You always want to show it on the C, Okay, so just keep that in mind. Let's denote that right here. So we're going to have our CN. Okay, exact same thing's going to happen. This is going to come in, attack our relatively positive carbon. This is going to get kicked off onto the oxygen. You're going to need to show the lone pair as well as the negative charge. And you need to show the curly arrow onto the proton here to form our alcohol. Now, the other thing here is that this hydrogen obviously was not involved in the reaction. So we have to switch this out for our cyanide ion. So we now have a nitrile formed. And we also have to do that in our final product. So let's pop that in, CN. And what would we refer to the functional group of our product here? This is a hydroxynitrile. Okay, try and remember that. Now, in our previous example, I told you that the H+ ion came from water or a weak acid. Okay, that is not the case for the nucleophilic addition of the cyanide ion. This H+ comes from a strong acid, more specifically sulfuric acid. Okay, so keep that in mind. Okay, next one is nucleophilic addition-elimination, and we're going to be dealing with acyl chlorides here. Okay, so acyl chloride. So let's start the mechanism with our reactant. I'm going to use the example of ethanoyl chloride. So that is our starting reactant. Now there's 4 nucleophiles we need to be aware of here. You're going to need to react with water, an alcohol, ammonia, and a primary amine. Those are the 4 nucleophiles. So let's begin with water. So we've got our water molecule here, the lone pair on the oxygen. Now if I asked you, explain what's going to happen next, would you be able to? Be honest, would you be able to explain what's happening here? Okay, hopefully you remember there's going to be a dipole existing here because the oxygen is more electronegative than this bonded carbon. So we're going to get delta positive, delta negative. Again, you don't need to show this in your exam, but you should understand it. And there's going to be a curly arrow going from this oxygen onto the carbon. Okay, and then this oxygen is going to accept the electron pair in this double covalent bond onto itself. Okay, real simple stuff. Hopefully you're okay with that. Now, intermediate time. Let's draw this out. So you have to show the lone pair and the negative charge, and then we have to show the bonded water molecule that just came on. Let's do that in green just to signify that. H. Now, can you guess what's going to happen next? What happened to this oxygen? What type of bond did it form? It formed a dative covalent bond. So it essentially lost 1 electron and sacrificed it in order to form that covalent bond. So it's going to have a positive charge, right? Now, this oxygen is going to reform the double bond. And this chlorine is going to be our leaving group. And it's going to get the hell out of the way, okay? It's getting out of there. And the reason for that is because this carbon, if this oxygen reforms the double bond, this carbon is now going to have 5 bonds, which is not energetically favorable. There's another dipole here whereby this is delta positive, this is delta negative. This is going to be electron withdrawing and suck the electrons onto itself and leave the molecule, okay? The carbon has 4 bonds again because this double bond forms, so it's a happy guy. This oxygen is going to accept the electrons from one of these hydrogens. Either one is fine, I just picked this one. And the hydrogen is going to go off in solution. It's going to unite with this guy and form HCl. Okay, hydrogen chloride gas. That's pretty much what happens there. What product do we have here? We're going to be having a carboxylic acid. Okay, now I'm going to run through the next 3 as quickly as possible because they're pretty much identical. So for the reaction with an alcohol, you just want to change one of the hydrogens on this water molecule to be some sort of carbon chain. So I'm going to use the example of an ethyl chain. So it's going to be ethanol right here. And you're going to want to follow the exact same principle whereby we have a CH2, CH3 here. Okay. And then our end product is not going to be a carboxylic acid. It's going to be an ester. Okay, just keep that in mind. Everything else should be completely the same. Right, and when we're dealing with ammonia, that's our next nucleophile. Let's change this up slightly and put NH3 here. That's going to come in, attack our carbon. The exact same things are going to happen. Let's rub out this, make it a nitrogen here. Very similar to with the water and the alcohol, one of these hydrogens is going to donate its electron back onto the nitrogen to make it neutral again. But these two curly arrows, exactly the same, no need to worry. What is our product going to be? It's going to be a primary amide. Okay, so let's draw that out. Instead of it being our ester linkage, it's going to be an amide linkage, whereby we have an NH2 molecule. Okay, this is our amide right here, our primary amide. Now, when we're reacting it with our fourth and final nucleophile, this is going to be a primary amine. Okay, so we're reacting it with a primary amine. Let's see what's going on here. So it would be our NH, and then we're going to have some sort of alkyl chain. So I'm going to use the example of ethyl again. So this is our primary amine coming in here and attacking our relatively positive carbon, exactly the same thing. This oxygen is going to accept the electron pair in one of these bonds, and we're going to form this intermediate. Now, the only difference here is instead of having an NH3 being bonded, we have our primary amine bonded. So let's rub out one of these hydrogens and replace it to be our ethyl chain, CH2, CH3, but exactly the same principles apply. Positive nitrogen, one of these hydrogens is going to donate its electron onto the nitrogen to make it neutral again, and we're going to get our product. But instead of it being a primary amide this time, it's going to replace one of these hydrogens with the ethyl chain. It's going to be NH, CH2, CH3. This is a secondary amide, also referred to as an N-substituted amide. And that is our mechanism. That is nucleophilic addition-elimination with our 4 different nucleophiles. Hopefully that was helpful. Let's move on to some aromatics now, and that should be our final mechanism that you need to know. Electrophilic substitution. So good old benzene, right? There's 2 different electrophilic mechanisms you need to know. We've gone through electrophilic addition for alkenes. You also need to be aware of electrophilic substitution. Okay? So this is our good old benzene molecule right here. Get comfortable with drawing these, all right? So you're going to either be having nitration, which involves the nitrate electrophile, or you're going to be reacting it in a Friedel-Crafts acylation reaction, where you're going to be reacting it with an RCO+. Okay, this R can be any kind of alkyl chain, and it originates from an acyl chloride. So just keep that in mind. This CO+ is due to it used to have a Cl, but that's been kicked off. And you need to know the equations for the formation of the electrophile, but I'm not going to cover that in this video. Just be aware that in both nitration and Friedel-Crafts acylation, we have a catalyst involved in the formation of the electrophile. That's really important to know, and you need to know the equations for the formation, okay? Just keep that in mind. So going back to our mechanism, let's rub this out and focus on what we need to know for our curly arrows. So we're going to have our nitrate ion, right? NO2+. I keep calling it a nitrate ion. It's actually referred to as a nitronium ion, okay? So keep that in mind, but the actual reaction is referred to as the nitration of benzene. So what happens here is this ring right here is incredibly electron dense, okay? So what happens is it is attracted to this nitronium ion right here, and we're going to be drawing a curly arrow from the edge of this ring onto the electrophile. Okay, that is our first step. What is our second step going to be? Going to be forming our intermediate right here. So let's draw this out. So first thing that's going to happen is this ring in the center is broken. You need to know how to draw that. Secondly, each of these carbons on the edge has a hydrogen bonded. So all the way around, there's one hydrogen bonded to each of these carbons in the skeletal benzene structure. So what I'm going to do is I'm actually going to denote that right here. So we're going to have our nitronium ion that just bonded on, and we're going to have a hydrogen ion, okay? Now, the way that we draw the broken ring is what we refer to as a horseshoe structure, okay? So, and something you need to keep in mind for AQA is you cannot pass the boundaries of the adjacent carbon. So for example, if we draw an imaginary line here to the center, and then out to this carbon here, you cannot cross that boundary. So for example, this ring would be incorrect because the horseshoe has crossed the boundaries of the adjacent carbons. Super weird rule, I'm not going to lie, but that is what it is. So what I would do is I would draw a horseshoe, keeping in mind the boundaries like this. Okay, it doesn't really matter. It doesn't have to be perfect. As long as you draw a horseshoe-ish shape and do not cross the boundaries, you're completely fine. The additional thing is because we formed a dative covalent bond with this nitrate, I keep calling it nitrate, our nitronium ion, there is positive charge here because it's lost negativity, it's lost electrons. So you'd have to denote that with a positive charge in the horseshoe. Okay, and what's going to happen here is this hydrogen, which is very common for all these mechanisms, is like, you know what, mate? You can fulfill your neutrality again, gain an electron from this covalent bond onto yourself, and I'll just get the hell out of here. Okay, so that's exactly what happens, and we're going to have our nitrated benzene as our product. And then the H plus ion is going to come off. Okay, I'm going to go over the final mechanism, Friedel-Crafts acylation, hella quickly, because it's pretty much the exact same thing. So let's rub out this nitronium ion, rub out this NO2, rub out this NO2, and replace it with our carbonyl. So it's no longer an acyl chloride. We're going to have a COCH3+. Remember, this doesn't have to be a methyl. It can be any sort of carbon chain, but for this example, I'm just going to use this. So this, again, this ring, this region of electron negativity, electron density is going to be attracted to this positive electrophile. We're going to be forming our intermediate here with our broken ring, our horseshoe structure. And then we're bonding on this molecule here, and we're actually going to be forming a phenyl ketone, okay? Ketone because we've got this carbonyl bond here, that's COO, and we bonded onto a phenyl group because this hydrogen has donated its electron into the ring to reform its neutrality, reform its electron density. So our final product is going to be this guy right here. A phenyl ketone, okay? And then again, this H plus that left the molecule is going to reform our catalyst, which in this instance is AlCO3, aluminium chloride, and fulfill its function as a catalyst, okay? That is every single mechanism you need to know. Hopefully it was helpful. If you have any questions, let me know down below. I'm really hoping I didn't miss anything, and I really hope that it helps you out. If you did find it helpful, smash the hell out of that like button. It really helps the channel grow. Hopefully through this entire video, you realize how similar these mechanisms are and how you just need to do some practice questions. Doing practice questions is so much better than memorizing the mechanisms, okay? You're just going to get a bit confused and get muddled up. So practice questions, memorize the reagents, conditions, observations, and equations that you need to know specifically to do with the catalyst. But other than that, just keep practicing, keep revising, and you'll be completely fine. Best of luck with your revision and upcoming exams, guys. Until next time, peace.